disclaimer here. What I'm presenting is my own work and of my authors and not of the opinions of my employer. So just to give you an idea of who we are, because there's a lot of Toyota entities out there, just to give you a brief idea where we come from. We are in Toyota Motor North America, and we work on future challenges research. So we are, I believe so, but yeah, I think I'm it. And so there is this institute, Toyota Research Institute of North America. And within that, there are several divisions, materials, electronics, and another one that is called future mobility. And within that, there is what's called CPS group, which consists of myself and my 3 collaborators, who some of them are here. Our mission is to develop systems that are risk aware and can come with guarantees on functionality and performance within uncertain environments. We have 3 main priorities: requirements, verification, validation, and certification. We do a lot of connections between requirements and certification and validation to the planning and control for heterogeneous multi-agent systems. And finally, a little bit of human-robot interaction, but not necessarily from the perspective of human subjects, but more kind of algorithmic. So that's kind of our agenda. So let's move on. Robots are everywhere, and this is a Toyota Takaoka plant. You have robots moving around the vehicles for assembling, robots in logistics warehouses and so on, and more recently, robots in hospitals. All these improve efficiency of the system, help in many cases with labor shortages, and so on and so on. And I would like to highlight here a recent article by some of our colleagues in Japan, where they published an article in their explorations and development of a production level system that is for hospital robots. And it's a good read to highlight how they encounter several challenges in that environment and how they overcome them in that situation. So for example, when you have robots in an environment, they might block a corridor, right? So this is a confined environment. You don't have corridors for the robots that are separate from what the humans are using. Everybody's working fluently together. So you are going to run in such scenarios, right? Another example is you may want to have event detection, scene understanding, see what's happening and what's going on in that environment. And finally, a lot of simulation to real and back testing and verification. Again, this is not our team's work. This is primarily our colleagues here who actually develop these products. But we are inspired by these challenges, and we are doing our own research, trying to push the frontier. So within that context, we work in all these layers of autonomy, from the global planner up here all the way down to the low-level control. And that's what I'm going to briefly discuss today, taking you to a brief journey from global planners all the way to low-level control, where I'm going to advertise our latest toolbox that's publicly available for control barrier functions. All right, so I'll start. Oh, and since we are just 4 people in that group, we are working a lot with collaborators. And so at the conclusions, I'm going to circle back and say we are always open to collaborations. Please reach out with ideas. And yeah. All right. So the first topic I'm going to present is actually the work of Kandai, who is here in the room. And we started, he did an internship with us 2 years, I believe, ago. And we were looking back then on how to learn workflows so that we can observe existing processes and extract information, and build models, and then optimize for cobots or any type of optimization we might like to do. Also, there was a follow-up work. When Kandai went back to his university, we continued working, and he's going to give a presentation on Thursday. So please follow up on that. Let me give you the basic idea here. So let's say you have a factory floor. workers are doing stuff, and you have a method to extract events that are occurring in that environment. This will typically look like time traces, which means you have an observed event, you have a time that event happened, and you have multiple of these. And what you would like to do is collect all this data and learn a timed model that would represent the constraints for that process. And it doesn't have to be linear. You can have partial order. So let me show you an example. In this very simplified example, we have an assembly line, and the car arrives. You will add glue to glue the window. Then you are going to lift the window, and then you replace the window. You release the grippers. And what you see here is a sequence of events or tasks that need to be performed. And this clean dust can happen in parallel, right? So you have events coming in, and you would like to construct such a partial order abstraction of the events coming in. And in addition, you're going to add timing constraints because these events are happening within certain times that you observe. You collect all this information, and you are going to add timing. You're going to add clocks that measure time relative to certain events. And your goal here is to collect all these constraints and then build a model that represents this with minimal number of clocks. Minimal number of clocks is an important constraint here because this is what you need to track at real time to make sure that you're satisfying that partial order graph or not. Okay. So I'm not going to go over the details here, but the overview is the following. You start with the data. You have your timed sequences. You create first a partial order of the events as you observe them. What do you think might be in parallel? What might be sequential? This is, again, from the events that you have observed. Then you collect all your timing constraints from the timestamps that you have observed. And you do some redundancy reduction to find only the essential timing constraints, because there's a lot of transitive properties here that you can take advantage of. And finally, you need to solve this combinatorial problem to cover all the timing constraints that you have with a minimal number of clocks. I'm not going to go here in the details. The details are in the paper. And finally, you get that graph with all the timing constraints and the minimum number of clocks that you would need. So the main result here is that we can learn graphs. So if you were naively collecting the timing constraints, this is with our approach. You can see that you need way less clock variables that you need to count time than our approach. Now, since I cannot present any factory data, I'll do the best closest match to that, which is the Overcooked game. For those who are not familiar with the game, you have, this is a multi-agent game where you have multiple agents trying to cook foods orders that are coming in. So I believe Kandai or somebody from the group did all manual annotations for the events that are happening here. But the fun part is the next slide. So you have on the left here the beginner's playing, which is typically myself when I play with my kids. They always complain that I'm too novice for the game. And the right one is the professional players. And here's the graphs that were extracted. And this is interesting. You can see the beginner's play is way more complicated. It starts always with new rise. And the beginner players don't take advantage of parallelism that exists naturally in the game. Whereas with a professional game, you can see that you start with a new phase, but also you have many tasks that are standalone, right? They can be executed in parallel depending on the initial conditions that you're starting with. All right. So that was promising. And then the next thing, the next logical step of that work is if you already have the time partial order specification for the problem they're trying to solve, can you assign or can you allocate different robots and distribute them so that you execute all these tasks optimally and you satisfy all the constraints, minimum, maximum time, dependencies of events and so on, and finish on time. Okay? And the answer is, of course, positive. You can do it. And that's what Kanda is going to discuss on Thursday. So please attend his poster and ask him questions about that. I'm not going to say anything more about this. I would like to highlight that he also did some nice experiments with rovers. Hopefully, he will have his laptop there to show the animation, the videos playing. I'm not going to do that. What I'm going to do is I'm going to move on to the next part of my presentation, which is socially aware navigation, right? So we described one method that we have been working on for taking high-level task missions and mapping them to plans for multi-agent robots. And now you need to take these and execute them in an environment where humans are present, and you'll have to navigate among humans. So there are many challenges here. I'm sure many of you are already working on such challenges. I would like to summarize them here. We have high uncertainty in the foot traffic, how many people are in that environment. Density of pedestrian traffic, I guess that's related to number one. Social expectations, potential physical contact between the robots and the humans, and finally, human-robot communication, so that we can start optimizing the performance of the system overall, human and robots, and avoid deadlocks and other disadvantageous situations. So here's an example. I already showed you an example with the hospital robot at the beginning, but here's a simulation. You have the robot is trying to make a left turn, but it's always been interrupted by humans who are completely ignorant that the robot is trying to make a left turn, right? So the robot tries to avoid it, avoid the humans. So we would like ideally to be able to plan for the robot, to plan the communication actions in the environment. So at some point you would like to say, oh, I would like to make a left turn. It doesn't matter what modality, communication modality you're using here. Are you projecting an arrow on the floor? Are you saying verbally, are you having flashlights going on or whatever? The question is, when do you plan to, and how do you decide what communication action you should be issuing? And this is work we have been doing with my former colleague and current collaborator, Sid Srivastava at Arizona State University. And we are continuing working along these lines. So the idea is the following. We do the classical motion planning paradigm. And on top, we have what we call a communication planner. So the bottom layer is the standard RRT, for example. It doesn't really matter. It is any standard motion planning technique. In this particular case, we use prior work we have done on rapidly exploring trees with control barrier functions as constraints to guarantee safety. But again, this is agnostic to that. This is just a method that we had available to guarantee safety at a low level. So we have the human motion model to predict the movement of the human from the perspective of the robot to build this tree. But on top of that, we have the communication planning layer, where here the important part is that we have a human sensor model, right? What the human may be able to perceive from where the robot is and what communication actions it has. Maybe it has some visual communication actions, maybe it has some verbal communication actions. It really depends. So what we'll have to do here, we'll have to have a belief update on what we think the human may perceive. So this is what the robot thinks, right? We'll have some cost function which depends on the goals of the robot. Maybe the human will have priority, maybe the robot should have priority. And we'll do a local search in the environment. And given these two stages, the robot will select a point in the human's environment and say, okay, I'm going to move towards that location, whatever communication action it is. And hopefully the human will collaborate and optimize the movement. So we did some simulation experiments. In this particular case, the robot has priority and tells the human, okay, I'm moving forward. The human is supposed to move out of the way. If they don't move out of the way, that's fine. We still have safe control at a low level, but nevertheless, we're trying to optimize the interaction. The second part, what you saw there, is that the robot did not have priority. Maybe the task that it was executing was not time critical, so it stays on the side and lets the human pass by. So it's not surprising that if you communicate, you reduce deadlocks, and this is what you would expect at the very least. And so you can also, by using social force model for the human motion, you can collect data numerical. You can argue, of course, whether this is realistic or not, but nevertheless, when the human collaborates, the simulation experiment shows that we can do much better in terms of proximity cost, how close you come to the robot, and deadlocks. So in many cases, in close, confined environments, if you don't have the communication layer, you can get in deadlocks. That also connects to the morning talk where you had communication between robots, and if you don't have communication, you can run into deadlocks. The same situation with human and robots. We have real experiments trying to move this to a little bit more realistic scenarios. This is a scenario that Mehdi, who is the lead author on that work, has done. Small environment, but it works on a real robot. So this is robot and human working next to each other. There's no interruption here. I think it's a little bit clunky as through Zoom, but you get the idea. You get the same behavior no matter whether the robot has priority or the human has priority. Things become a little bit more interesting when you would like, for example, to go to the whiteboard. You tell the human, I'm going to the whiteboard. The human hopefully understands that and moves out of the way. So that's the experiments. I'll skip now the rest, just to give you an idea that there is progression into that. And I'll go now to the low-level control layer, where we do risk-aware motion planning. Again, in human-occupied environments, the uncertainty is higher. There is higher risk, and we need to somehow accommodate for that. There is a lot of work along this direction, maybe too much to kind of try to summarize it. But from our perspective, what we have been doing, we have been developing control barrier functions that take into account probabilities and risk and so on. So let me give you just a brief presentation of the setup here. We assume that the robot itself is a deterministic agent, has full control of its actions, but the environment is non-deterministic. In particular, all the dynamic obstacles that are operating in such an environment can be modeled through stochastic differential equations. And you may want to model neighborhoods of humans in case you have social constraints that you would like to take into account, and so on and so on. And our goal here is to compute control actions, paths, such that the probability of collision within a finite amount of time is bounded, and is bounded by something we choose, this probability upper bound here. We use control barrier functions as a filter. We take your classical pipeline for control, and you can have here, of course, perception, state estimation, and all these other typically stochastic frameworks. And you're going to add the safety filter as a control barrier, as a risk-aware control barrier function to try to optimize with respect to a reference trajectory produced by the pre-existing control system, so that you satisfy your safety constraints and bound the risk to the desired level. Okay. Typically, this is how it looks like. You have a quadratic program, you have a bunch of constraints so that you can bound the risk. And depending on the exact method that you're using, you're going to get different mathematical formulation here. And every paper we write has a different controller here, so I'm not going to go into the details. The reason I'm showing that is that what we are trying to do now, and that's the toolbox that we released, is to make this easy. So we would like to be able to have people code something with a control barrier function, risk or non-risk aware, within minutes, hopefully. So that's the next step I would like to present here. It is our new toolbox, which we just released on control barrier functions. We utilized functional programming primitives, so everything is encoded within the functions that you are using. We assume that you're going to give a controller, the system dynamics, any state estimator that you might be using, integrator for the simulation, perturbations if the system problem is stochastic, and any sensor model that you're using. So this toolbox was primarily developed by Barth and Mitchell, and we asked another intern to use that toolbox without having seen it at all as a proof of concept that this should be easy to use. And what we asked him to do is to just implement a very simple collision avoidance controller for two single integrators. So you can think of these as two individual robots. He did that within 1 hour. So he downloaded the toolbox, read the manual, read the tutorials, and implemented this system within 1 hour, starting from scratch. On the other hand, you have to keep in mind, of course, that he's a control barrier function expert. So even though he has not seen the tool before, he definitely knows what he's doing, right? So you import the JAX because we do a lot of symbolic manipulations to compute all these gradients and constraints. We import our model. You encode the dynamics and the control matrix for this two-dimensional system. You have here the nominal controller, because we do need a controller so that we can add on the safety filter afterwards. Now we add the state constraints for the problem. In this particular case is that the robots should not collide to each other. You should have always some distance between them. We add the Lyapunov functions. You have the capability to add Lyapunov functions so that you have a goal also as part of your control architecture. And that's it. You generate a model, and then you simulate. You simulate, you have your simulation parameters, whatever you like. And this is standard. You just feed all these things you computed in the right functions. Important to note here that I have removed the noise generation. So I'm assuming this problem is completely deterministic, but you could do very well add noise to the system. And so you run the simulator, and that's what you get. All these were done within 1 hour from scratch. Download the Docker container and run the simulation. So we hope that this can be a way to speed up the development of these tools. And also we hope, as we keep adding benchmarks, that this might become a toy or a kind of a sandbox for comparing different control barrier function techniques. All right, also 10, he easily did also 10, and now he has it in a parameter, so you can do an arbitrary number of robots. Closing remarks, I just presented a very small picture of what we are trying to do. I've not talked at all about our efforts to do testing, verification, certification, and so on. This was more about from the perspective of how we can start do risk-aware deployment of multi-robot systems in human-occupied environments. I would like to thank all of our collaborators here. We are also always looking for collaborations on validating, verifying performance verification, trustworthiness of AI-enabled systems, and embodiment and CPS design exploration. And I'll stop here. Thank you. And I'll take any questions if there are any.
Thank you, Georgios. Very, very interesting talk. If you have time for some questions, you can come up to the mic.
Great talk. I guess you talked about some challenges of navigating closer on humans. Have you run into any infeasibility issues as you have more uncertainty and as the number of humans increases in the shared space? If you've encountered any, and how did you think about?
Right, absolutely. That's a good question, and I guess it's not a surprise when you deal with the control barrier functions. Are you referring to the control barrier functions or the other layers of planning, the stop?
Mostly the control.
Yeah, controls. Yeah, we do, and we have been working on experimentally reducing this infeasibility. We have a couple of papers ongoing, hopefully will come out, that we reduce substantially the amount of infeasibilities that occur by controlling the feasible space also as part of the control barrier function. So not only you add the safety constraints for all individual agents in the environment, but you also try to control how the volume of that feasible space evolves over time. So we are very hopeful for that approach. And then the other thing we'll be working on is kind of an architectural mechanism to take to reduce this type of infeasibilities. But yeah, this is an existing problem.
Thank you for the talk. So for the CB-MPC toolbox, you just showed the last animation. So let's say we have two agents which are want to avoid each other with physical velocity. But in the symmetric case, isn't there any networks situation? So let's say the animation you showed one agent choose to connect another agent choose to.
Right.
Yeah. So. Yeah, my question is, in this case, you inject some random noise to make them like, or just have some.
Yeah, you're right. and you know very well what's going on here. So this is just a demo to show that you can do it quickly, right? This is not research problem. Okay, just to highlight that. This is just for us to show that, oh, you can do this within 1 hour, starting from scratch. That's all it.
Another question is that the physical velocity you showed in social robots. So you basically also have like a trajectory prediction for human.
Right.
And you like have a prediction error bound for
right.
guarantee on that. Okay.
Right. So, for example, when you have Kalman filters for doing that prediction, or when you have probability distributions, you can add constraints to take that into account. Yeah, we have papers on that. Thanks.
Thank you so much for the presentation. So maybe following up on that one short question, does the tool also treat automatically the problem of discretization? So for instance, if you have too large of a time discretization, you might actually be unsafe in between the updates.
Right.
So
no, we didn't do that. All right.
Thank you.
Good feedback. Good feedback. We'll be incorporating all that in the future. Thanks.